A very good afternoon and warm welcome to all for 11th day of Faculty Development Program on Emerging Research Trends in Computer Science and Engineering. Myself, Rednam S.S. Jyoti, working as an assistant professor in Department of Information Technology at JNTU GV, University College of Engineering. It is my distinct honor and privilege to introduce our esteemed resource person, Professor M. Shashi Ma'am, for today's Faculty Development Program. Professor Shashi Mogalla is a professor in the Department of Computer Science and Systems Engineering at Andhra University. With 30 years of teaching and 7 years of research experience at the university, she contributes to both academic and research activities in her field. As an associate professor and assistant professor, Professor Shashi Mogalla is likely involved in teaching undergraduate and postgraduate courses in computer science and systems engineering, conducting lab sessions and guiding students in their academic pursuits. Professor Shashi Mogalla's research areas include computer science, artificial intelligence, machine learning, data mining, and deep learning. Professor Shashi Mogalla holds an ME in Computer Science and Systems Engineering and a PhD in the same field, both from Andhra University, obtained in 1985 and 1994, respectively. Professor Shashi Mogalla has published 119 papers in international journals. These papers cover various topics such as an efficient malware detection framework with the stacking assemble model, Android malware detection using multi-layer autoencoder and random forest, high utility occupancy sequential pattern mining algorithm based on utility occupancy framework, a survey on machine learning for cybersecurity, and many more. Professor Shashi Mogalla has received several honors and awards, including Best Teacher Award in Engineering in 2016 from AP State Government and Young Teacher Award in 1996 from AICTE Government of India, Best PhD Thesis in Engineering and Science in 1995 from Andhra University. Professor Shashi Mogalla gained membership in professional bodies such as Fellow of Institute of Engineers in 2021, Life Member of ISTE, IEEE Computational Intelligence Society. Madam participated in the committees such as a member of College Research Committee, AUCE, chairperson of Faculty of Engineering, Andhra University, member of Andhra University Academic Senate. Under her guidance, 25 members are got PhD degree. Professor M. Shashi Ma'am is working ongoing research project on the topic of information security, education and awareness, which is funded by Ministry of Electronics and IT, Government of India, with sanctioned amount of 75 lakhs from 2016. Now, I would like to invite our today's resource person, Professor M. Shashi Ma'am, to deliver her talk on natural language processing. And I am very fortunate, or I am very thankful to Professor Jayasma Ma'am to give an opportunity to introduce such a great personality. Thank you, Ma'am.
Thank you, Dr. Jyoti, for your good words about me.
Thank you, Ma'am.
Thank you, Jayasma, for organizing this knowledge sharing event. And I'm glad to share my knowledge on natural language processing with our peers working in different colleges. I came to learn that the participants are already teachers or associate or assistant and professors from different engineering and computer science colleges. So, am I sharing PPT? Is it visible to you? Okay. Yes, yes. So, in order to prepare this PPT, I have extensively used the course material from Stanford University. The material was prepared under the team of the senior most Professor Mannings from Stanford University. He is working on machine translation profoundly. He is known to all the researchers of natural language processing, especially the machine learning applications. I'm using those PPTs, that means lecture slides, to some extent, and I have added my own improvisations or modifications so that it suits to our requirement, because we can't go through whole of the course, isn't it, in this particular limited time of 3 hours. So coming to the topic, the natural language processing, it is the most happening field of computer science nowadays, because so many changes are occurring in this field. You all know the revolution created in information retrieval or usage of computers by the non-computer, even non-computer, that means lay persons, due to level of or availability of ChatGPT. Okay, so that is one of the examples. Like that, we have seen the Alexa, which will be responding to the needs of the users in day-to-day lives and gives advices and reminds you of things and does certain tasks as you assign to it, like switching on or starting certain appliances automatically at a specific time. All these things are happening only because of the success of NLP research. Now, in today's talk, I'll be going into some of the building blocks that are required for building NLP solutions for interesting tasks. What is NLP? It's the area of computer science that deals with methods to analyze, model, and understand human language. Human language is the natural language. It can be either English, Telugu, Hindi, whatever it is. Okay? So all those natural languages will have certain characteristics. That means the grammar is only what do you say, descriptive. That means it provides certain guidelines, but just because a statement made by a person is not perfectly grammatical, you can't totally deny that I don't understand because your sentence is not grammatically correct. Whereas if it is the computer language, the formal language, the grammar is a must, okay, mandatory. So because of this variation between formal language and human languages or natural languages, the difficulty level in dealing with human languages is much, much higher compared to just constructing the compilers or interpreters for formal languages. Now we'll go into the details. The natural language processing has become an inevitable component of most of the intelligent applications. Some of the applications are given in this particular table. The categorization according to core tasks into 3 categories. One is core tasks that are totally dealing with just language. The second thing is general applications, and the third one is industry specific applications. Under the core tasks, you have the text classification, information extraction, conversational agents, information retrieval, question answering systems, machine translation. This list continues, but some of the important tasks were listed out. Under the general applications, you have the natural language solution plugged into a bigger software. That means the software by itself is not aims. It doesn't aim only to the natural language processing, but it goes beyond. And the natural language processing task is a component in it. So it is like the personal, as I was talking about Alexa, the personal assistant, and similarly the search engines, and then some quiz games like Jeopardy, which was won by IBM Watson by appropriately developing a question based on the clues, given set of clues. So it definitely requires intelligence, and only because of the success of AI in association with natural language processing, the IBM Watson could reach such a successful champion level. Okay, similarly, the spam detection and learning analytics, that means plagiarism check, then tailor making the learning sessions according to the slow learners, the fast learners, and the special assistance required learners. Okay, so all these things are possible with the help of natural language processing solutions in a bigger application. Another scenario is the industry specific applications. So the specific to the industry, like if you can take the social networks, lot of social media data will be available. From that, you will be able to learn what are the most burning issues in the minds of the people, or the political scenarios, etc., etc. Similarly, the trends can be predicted very successfully by properly processing the contents of the social media data, like Twitter, etc. Next, the retail catalog extraction. Similarly, health record analysis. All these things are the other fields where, that means medical field, and then the financial field, that means the stock market, how they are going to be affected, positive trend, or is there a negative trend, etc., etc. All these things requires processing of lots of text. And then similarly, the legal entity extractions also. Most of the NLP tasks have open-ended solutions. Open-ended solutions in the sense, if you take a machine translation, given a sentence, different people translates the same sentence in a different way. Okay, so the solutions are open-ended and hence are solved using different alternative approaches. Yes, is there any problem? Am I audible? Okay. So the common NLP tasks in the increasing order of difficulty are listed out here. It starts from the spell check, simple spell check software, and it is the most less complex, easiest among the NLPs. And the keyword-based information retrieval, like Google, and then the topic modeling, like given a document, what topics are discussed in it, or given a news, what is the topic of that particular news, etc. Similarly, the classification of text into multiple languages so that you can select the specific repository in order to handle the content of the text. Next is sentiment analysis. This is again comes under the classification of text when you are processing the reviews expressed as text. Next is named entity extraction or recognition. Named entity recognition is a famous thing. So here, given a text, the words will be categorized into known classes like person, location, organization, etc. Similarly, the semantic role labeling, that means who did what and when a particular event has occurred, etc., and who were affected. All these things will be answered. Then only it is possible to get an answer for a query. Next is closed domain conversational analyst. Here will be like a answering system at a particular desk, so that the questions that were posed will be automatically, frequently asked questions will be maintained by the vendors. And if you ask a question that is related to that particular domain, then only they will be in a position to respond. So there will be a fixed set of questions, or the question should be related to a specific topic. Then only the conversationalist will be answering those questions. So this is a simpler level. Whereas at the end of the spectrum, you have open domain conversational analysts like chatbots, which are more general. That means like ChatGPT. It will be able to answer most of the questions that you will ask for. Okay. Similarly, language modeling, that means when you are typing a sentence, the next words in the sentence will be automatically suggested. Okay. So that is only based on the language model. And text summarization, that means given a big document, the gist of the document will be automatically extracted by the natural language processing software. So that task is text summarization. And question answering like Watson, or for that matter, there are several question answering systems. Again, this is an open-ended, because a question can be answered, especially certain questions can be answered in multiple ways. So this increases the difficulty of the task, because if there is a single solution, it will be easier to arrive at it, to aim at it, and build the model according to or towards that particular aim. When the solution is open-ended, then it will be very difficult. That is how in the spectrum, the question answering and the machine translation and open domain conversational analysis stays at the level of complexity. So these are different natural language tasks that are being successfully handled nowadays because of the developments in the machine learning, deep learning, and the building blocks provided by those fields in terms of the RNN with LSTMs and transformers, etc. We'll go into the details of those things in the later part of the lecture. Now let us start the technicalities, that means the concepts, the basic concepts. The human language and the importance of the meaning of a word. The human language is expressed in terms of meaningful words in order to constitute sentences. Now, the word representations that can capture the meaning is essential in the process of natural language understanding or generation. Okay, so natural language processing involves both understanding the text or the capability to generate a text according to a specific context. But this particular lecture concentrates on natural language tasks that deals with text only, though the same principles can be extended for the spoken language processing as well. For spoken language, in the beginning, will be converted into the text form, and all the steps handles the text will be continued, they are applicable. And finally, when you are giving the output, if required, again a conversion step will be there to convert the text into again an audio speech signal. Next, the traditional NLP software was implemented using language-specific heuristics. For each language, there will be certain grammar. English has its own grammar. Chinese has its own language, grammar. Similarly, Telugu will have and Hindi will have different grammars. So, given a specific language, it will have certain heuristics. So capture those heuristic rules, and accordingly this software is built, making use of the repositories associated with that particular language, like the meanings, the dictionaries, the lexicons, and thesaurus. Okay, if you take English, the word net is the thesaurus that consists of the synonyms and hypernames. Synonyms means alternative words. Hypernyms means it is the more generalization for a specific word. Okay, in addition to the meaning and the parts of speech, tagging of a given word. So, given all these repositories, the traditional NLP softwares implements the heuristic rules of that particular grammar rules, etc., in order to understand the natural language of that specific language. Okay, there are limitations for this approach. The limitations of the heuristic based NLP are maintaining this word net is very cumbersome because it is very specific to a language. That is the first thing. And second, it provides the list of words which are synonyms. But that doesn't mean any of the word can be replaced by another alternative word provided in the synonym. Just because it is a synonym, you can't just replace that word. Both of them doesn't mean exactly the same. They will have subtle differences, and certain words will fit in certain contexts. Okay. Similarly, the word net cannot automatically handle the changes in the trend. Okay, as the days pass on, certain words will be used by people for certain purposes. So such trends cannot be captured automatically by the repositories like WordNet. Similarly, certain words may not be available in those WordNets because the natural language can be enumerated exhaustively. Okay? Some words will remain beyond the vocabulary that is formed by the humans. Next is, it requires human labor to create and adapt. Okay? So people has to collect information and then maintain the repository. And then it is subjective. That means whether proficient is a synonym of good or not is a subjective matter. For some people, they may feel that both of them are exactly the same. For some other who are very, very critical may not feel that both of them are exactly the same. So it depends on the specific people who have developed the repository. And then they cannot be used to accurately compute word similarity. This is very, very important. So in order to find how similar two words are, there is no clue by these word nets. By including a word in the synonyms of another word, it will say yes. If it is not included, then it is absolute no. there is nothing in between. That means if the words are close, whether the words are close enough or not. Okay, if you take college and school, whether the words are close enough or not depends on the context. We're talking in a broad perspective of education. Whether you say it's school or a college, it is one and the same. But when you're talking about a specific case of a child going to school or college, there may be a lot of difference. If it is a kid, then he will go only to school. He will not be allowed into a college, isn't it? If it is a 20-year-old, he is not allowed to sit in the school, the normal elementary or high schools. Okay, I'm not talking about School of Computer Science or something. School word is being used for different purposes. That is the trendy use of trendy changes in the meaning of a word. Okay, now the trend is to use a school for a general purpose educational institution rather than a educational institution that nurtures small kids below 10th. Okay, and it differs from location to location. If you go to another educational system, again the meaning will change. So such changes cannot be automatically incorporated into the repositories like WordNet as the time passes. So you again have to employ humans to make the corrections on a intermittent or periodic manner. Okay, those are the drawbacks of the heuristic approach compared to making use of machine learning techniques and automatically trying to process the large amounts of text and learn from them. Okay, so here representing the words as discrete symbols. Each word can be represented as a discrete symbol, and then whether that symbol exists or not only matters. That is how these words will be represented as one-hot vectors. So the length of the vector will define the size of the vocabulary, So if you're dealing with 10,000 words in the vocabulary, which is very, very small, each word will be represented as a bit sequence of 10,000 bits. Okay, in which only one that corresponds to the position of the word in the vocabulary will be marked as 1, and all the rest of the positions will be filled with the zeros. That is called one-hot encoding of words. Okay, so when you're considering words as discrete symbols, one-hot vector representation is extensively used. But here, the dimensionality of one-hot vectors limits or fixes the size of the word vocabulary. If new words arrives, you have to change the coding for all the existing words also. It is not just adding those new words. Okay, that is the problem with handling words as discrete symbols and representing them as one-hot vectors. Next, keyword search in that representation may not find relevant documents due to orthogonality of one-hot vectors of different words. So if you are searching for a word which is slightly different from the word that is already existing in a document, you can't find that document just because of the difference between the word that is existing in the document and the word that is given as a. So this can be overcome by making use of the synonym sets available in the repositories like WordNet and extend the query, that is called query extension or expansion, And if directly that word is not there, that is, there is no match for that particular query word, query term, check for the documents that have the related words. So that will solve the problem to some extent, but still there is no, it is not possible to assess the distance between a pair of words as it can be done in the more recent methods using machine learning. Okay. Next comes So the solution to this is go for the context-based representation of the words. So it believes the rationale behind context-based representation of the words is the meaning of the word can be captured or can be identified based on the words that occur around the central word of interest. A word's meaning is given by its context, captured by the words that frequently appear within the window of fixed size. If you take banking in this example, in order to find or represent the banking, you don't represent the banking as a symbol like you did in case of discrete representation of words. If you go by context. So what you will be doing is the representation of the banking is obtained by considering the words that occur before the banking and after the banking within a vicinity of say 5 words. So here take 5 words, 1, 2, 3, 4, 5. 5 words, that means starting from the government until into. Similarly, the next 5 words. Okay, crisis has happened in 2009. So all these words will be considered. Similarly, it's not enough to take one specific context. This is a single context. You need to process several occurrences of this banking and consider for each occurrence what is its context and take or try to capture the gist of the context and based on words that frequently occur in most of the contexts along with banking. You will be representing the word banking so that the distance between a word and the words that generally occur that go with this word will be less. That means they are considered as similar words. Okay, so the words occurred within the window around the word are context words and they represent the meaning of the central word. In this example, banking. So like that, the word vectors, that means the words are represented as vectors which are dense such that it is similar to the vectors of the words that appear in the similar context. So when you are forming a word vector to represent the word, the information that is considered is, the data that is considered is the words generally occur in its window. Okay, in its window most of the times. So because of that consideration, the distance between the word vectors of similar words will be less. So here we will build a delta for each word such that it is similar to the vectors of words that appear in similar contexts, measuring similarity as the dot product of the word vectors. How do you assess the similarity? The cosine similarity. Generally, the cosine similarity is accepted as a metric for estimating the similarity of vectors. If the angle between two vectors is less, the cosine of that cosine similarity of those vectors will also be small. Okay, so this is indicated in this particular figure, and such word vectors are called word embeddings. So once word embeddings are learned, you are no longer constrained to fixed sized one hot representation, one hot vector representation of the word vocabularies. Okay, so if new words are to be included, you can always include them by considering or processing the text that includes those words. Okay, so here in the word embeddings, if you look at this picture, this indicate the king. This is one vector representing the king, and another line, another red line indicating the man. Okay, now the distance between these two, the angle between these two. Okay, so this is indicated as king minus man. Okay, so this is again another parallelogram, the queen minus woman. And this line indicates, the dotted line indicates the distance between queen and woman. Both of them are same. That represents the ruler. The ruler is either king minus man or queen minus woman. Okay, both of them are equal. So that is indicated by this yellow line. So if you remove the gender from king or queen, you will end up in ruler. Okay, similarly you can do the other arithmetic, vector arithmetic, like this. Once you are in a position to represent the words in the word space as vectors. Okay, so the next comes, so this is most of the NLP tasks makes use of word embeddings. Now, how to learn word embeddings? The famous step towards learning word embeddings was successful with the advent of word-to-vec framework. So the word-to-vec framework in 2013, I think, it gives you every word in the fixed sized vocabulary is represented by a vector. Okay, so how do you do that? Process a word at each position T in the text, considering it as a center word C compared to the context words O within a fixed sized window. So what did I say? In order to represent a word, you need to consider the context. How do you define the context? Context is nothing but the words around it. The words generally occur around it. So here, all of these 5 words before and 5 words after the banking in a different occasions. These are all defined. They will define the context where the banking occurs. So here we are trying to capture the general context, and accordingly we are trying to get a good representation for banking such that the similarity between banking and related words to the banking will be minimum. And if the similarity, if you are assessing the similarity between banking to unrelated words, it will be very, very less. Okay, the words which are related will have high similarity, and words which are not related will have less similarity. Okay, so in order to do that, what you will be doing is use a similarity of the word vectors for C and O to calculate the probability of O, that means an outside word, given the central word. O for outside word. Outside word means the words that fall in the window around the central word C. Okay, that's the coding. C and O. C stands for the central word for which you are trying to form the representation, and O forms the word, O denotes the words that occur in the window around the central word C. So keep adjusting the word vectors to minimize this probability. So pictorially it is shown. If you, for simplicity, we are taking a window size of 2, that means 2 words before and 2 words after. For a central word, banking would be considered in this case. So the process of estimation, estimating the probability of a central, what is to be estimated? The probability of the outer word given the central word. Central word is already known. So these are the words that occur in its vicinity. That has to be estimated. So the probability of each word that is outside given the central word, that is WT. The probability of WT plus J given probability of given WT. So it is the conditional probability of WT plus J given WT. This will be estimated. This needs to be estimated. Okay. So in addition to this particular terminology, you have to look at the representation of the word. It has two vectors. One is a vector VW when the word is considered as a central word. UW when the word is considered as the context word. Context word means outside word. Okay, here the words that are shown in pink are the context words, and the word banking that is shown in red is the central word. So that has to be remembered. Next, we'll go towards estimating the probability of an outside word given the central word. So this has to be estimated. How do you estimate it? By taking the representation of the word. So it is like start from a random representation and then goes on improving the representation iteratively until you will get the minimum value for the objective function. We'll look into it step by step. Okay, so now the probability of an outside word given the context word, given the center word C, is equal to exponentiation of, it is the softmax, exponentiation of U0, UO. What is UO? It is the representation of the outside word when being used as outside. So it's a word O, and the component of it, which component you are taking? The component that corresponds to usage as outside word. Okay, so for the same word you will have both VW and UW for the word W. Okay, so you will be using U part when the word is being considered as an outside word, and you will be using V part when the word is being considered as a central word. So accordingly you will be using those parts. So UV, UO into VC. Okay, so for this you will be applying the softmax. What is softmax? It is like exponentiation of xi divided by sigma over all j starting from 1 to n exponentiation of xj. So this is the general formula for softmax of xi. So for like that, apply softmax. Yeah.
Ma'am, what is meant by U not transpose? We have U, W and V, W only, ma'am, for outside and the center.
This is transpose. T means transpose. In order to make it.
Okay, ma'am. What is
Yeah.
U naught? U naught.
U naught. U naught is, here W is the word in general. The word can be an outside word or central word. Okay? You are estimating, in the process of estimating or preparing the representation for a center word like banking. You will be considering all the words that are around it. Okay? Within a window of size 5 or 2. Like it was shown here. So the W
Okay,
is
ma'am.
in general, it can be either these words, pink or red. If the W is red, then we'll consider it as a center word. Okay. So in that case, we'll use V part of the representation of the word. If you're considering these pink words, the word shown in pink, then they will be the context words. For using them, the representation part, U part of the representation of those words will be used. Got it? Got it or not?
Yes, ma'am. Yes, ma'am. Thank you.
Yeah. So the
Yes, ma'am. Yes,
representation
thank you.
has two components. So appropriately, we'll be using based on the role of the word, either as a center word or the outside word, we'll be using the specific component. So if it is being used as outside word, we'll use the U component. If it is being used as a center word, like C, we'll use the V component. Got it? So in the whole of this occurs in the process of estimating or preparing the representation for the center word. Okay? So this is a step. You need to estimate for all outside words, wo, given the center word, you need to estimate the probabilities one after the other. If you are considering a window of 2 back and forth, that means 4 outside words will be there. For each of those words, you have to estimate the probabilities using this particular softmax function. Got it?
Yes, ma'am.
You will get better clarification in the next slides. So here, once the probabilities are estimated, so here you are using the probabilities of all the outside words given the center word. So here you are trying to estimate the probability of the word at position T. Okay, what is the T? T is for all T starting from 1 to capital T, where capital T is the length of the text that is being processed. Okay, what you need to do is the likelihood of finding a specific sentence with those words. Okay, you have already have a sentence or multiple sentences, one sentence after the other. So the whole of the likelihood of that particular text, it is almost like the training set. The likelihood of this explained by the present values of theta. Okay, so what is theta? Theta is all the variables to be optimized. Okay, here these are the theta includes the representations of the words. That means U's and V's. Okay, they are to be updated iteratively. So given the representations, estimate the probability of the outside word at jth position or j positions away from the center word at T. Okay, so here this will be used repeatedly and you need to apply pi operation for all j starting from -m to +m. That means for all values which are back for all the words that are, this is -2, this is -1 and this is +1 and this is +2 positions. Okay, except j is equal to 0, all values of j starting from -m to +m, where m is the size of the window. That is what is explained here. Got it? minus m less than or equal to j less than or equal to n. 0 as a value. You need to multiply the probabilities, and you have to do it at each and every position. That means for all words, considering them as center words, starting from t is equal to 1 to the last word, the first word to the last word. If you multiply all these things, you will get the total likelihood, and this has to be maximized because you need to, the parameter set that you are learning should explain the contents of the text. So in order to explain it perfectly, the likelihood should be maximum. This is a general machine learning methodology, aim. So a better way for pragmatic advantage is to go for average negative log likelihood. So how do you convert it? Average means 1 by t because there are t positions, capital T positions. So it is 1 by t into this one. And negative log likelihood, if you apply log function to the probabilities, which are fractions, you automatically get negative value. So again, if you apply negative, you will get a positive outcome. And this positive outcome of the average negative log likelihood should be minimized. That will be the final objective. Okay, so our aim is to maximize the likelihood or maximize the predictive accuracy. So in order to do that, you need to minimize the objective function, which is nothing but the negative log likelihood on the average. So this will be the aim. You need to go iteratively by changing the values of the theta in order to minimize this particular j theta. Okay, so in this way you will proceed. And find the representation of words. Okay, the V part and U part are redefined at the end of each iteration so that always you will be reducing the value of the objective function until it becomes the minimum value. It reaches its minimum value. That is there in all learning tasks. You can apply SGD or whatever may be the technique depending on the methodology you use. Okay, so there are two variants for word to vec model. One is skip-gram, the other one is continuous bag of words. The skip-gram approach presently we have discussed in detail is it predicts the context words as position independent bag of words based on center words. So what you are doing here in the present situation just now, you are predicting, that means you are estimating the probability of the context word O given the center word. So that is gram approach. Predict the context word as position independent bag of words based on the occurrence of a center word. Whereas in case of continuous bag of words, it's the reverse. Predict the center words in a given context expressed by a set of context words. So here the probability of the center word will be estimated given a context. Given context means context is always represented by the words in the window. That means outside words. Okay, so the details of the skip-gram are already discussed. Similarly, you can have the continuous bag of words, that means CBOW, as an alternative way of estimating the probabilities of words. Similarly, you have like word to vec model, you will have GLOW model, which is equally popular or even more popular nowadays in order to provide the word embeddings for almost all the words in English. Okay, the Glow is developed by Google Incorporation, and they are also successfully developed word embeddings, which are very much useful for most of the NLP applications. Next comes another aspect is when you're dealing with words, you will have multiple senses for a word. If you take a word dish, it will have different meanings. Depending on the context in which you are using that word dish, you have to understand the meaning of that word. So that is called polysemy. Okay, often words have multiple meanings and senses, which is referred to as polysemy. And depending on the context, humans very easily interpret the words. You don't struggle in order to understand the meaning of a word, even if the word has multiple meanings. But whereas when you are doing it as part of NLP software development, you have to take it as a challenge. The polysemy poses a challenge for NLP systems unless the word embeddings are appropriately generated. The frameworks like Word2Vec provide word embeddings which are linear superposition, means simply the weighted summation of multiple senses of the word. Why? Because you are considering all the contexts in which the word happens or occurs, while in order to form the word representation. If the word occurs more often in a specific context, then more weightage will be given to that context. That is why the weighted sum of multiple senses gives you the word representation. Okay? Next comes a specific application, that is named entity recognition as a classification problem. So in this, the task is to find and classify the names in text. So you need to identify the names in the text and then classify them into different categories by labeling word tokens. So here, the sentence Samuel Quinn was arrested in the Hilton Hotel in Paris in April 1989. This is the sentence. In this, you must be able to identify the names, that is Samuel, Quinn, Hilton, Hotel, Paris, April, and year. All these things are considered as names, and each of these names are categorized into, that means labeled into appropriate class. Okay? The use cases. Tracking mentions of particular entities in the document. So given a document, you can identify where a specific entity, maybe you can search for a location or search for a person or a date, etc. And then similarly for question answering, answers are usually named entities. So in the process of answering questions, the question may be for a person or a location or a date or something like that. So if you have already a named entity recognition system, you can use that or in order to answer the specific question that is answered, that is to be answered. Okay, so these are the use cases. Just wait. Simple approach for an NER. So in the simplest approach, you need to recognize the category of a word. Okay, for that, you need to classify the word based on the context words in a fixed size window. around it. Okay. So in order to classify, either you can go for binary classification or multi-class classification. If you apply binary classification and more number of classes are there, then you have to repeat it for each class. That means you need to, in order to identify locations, you have to develop a model separate from identification of persons and separate from again identification of dates, like that. If it is a multi-class classification, you can do all those things, 3. That means given a word, it will be classified into either a location or person or date. So in this example, classify Paris as a positive or negative example of location in the context of the sentence, a window length of 2. So then the simplest approach, what you will be doing is, if you have to classify a specific name like Paris, you will be considering the words that occur prior to it and after it within a window of length. That means in this case, starting from the museum and in, you will be considering up to amazing. So this particular part of the text, only that is considered. Hence, what you will be doing is, the input for classification is the concatenation of the word vectors in the window. So the X for Paris will be the concatenation of the word representations that fall in the window of size 2, as shown here. So X window is equal to X museum. X museums means it is the representation of the word museums. And again, representation of the word in. Like that, concatenation of all the word representations for 5 words will be taken as the input. And then you will build a classifier. So that is inputted. The concatenated input is given here. X is fed here at the lowest part. And then the hidden layer, it takes the weighted sum of the inputs, that is Wx, and adds a bias B. And for whole of this taken as stimulation, you will apply a non-linear function. Okay? So nowadays, ReLU is extensively used as a non-linear function. If not, you can apply a tan H or some other logistic function for F. And once this is finished, you will get the outcome of the hidden neurons. And this hidden neurons represented as H. The output of hidden neurons again will be multiplied by another weight matrix, and in order to get you yes. And finally, at the output layer, if you apply the sigmoid function, because it is binary classification, you will be preferring to go for sigmoid function. If it is a multi-class classification, you would be going for the softmax function, so that you will get probability of belonging to a positive class in case of binary classification, or the probability of belonging to different classes in case of multi-class classification with softmax output expression, output function. Okay, that is here at the jth level. Okay, this is how generally the language classification can be done. Now, language modeling with RNN. So this task is very, very simple. At the beginning of the lecture, I showed there are certain tasks which are simpler, and there are certain tasks which are slightly more complex. And as you go down the list, more and more complex open-ended solution problems will be handled. So language model is capable of predicting the next word in the text based on the context captured by the previous words. Okay, so the text segment that defines the context is not of fixed length. So depending on at which position you are in a specific sentence at the time of prediction of the next word, the length of the context, that means the context is defined in terms of text of varied lengths. Okay, so that is the one of the characteristics in the language model. Next, the feed-forward neural network can handle fixed length inputs only. So you all know what is a feed-forward neural network. In the feed-forward neural network, you will have an input layer followed by one or more hidden layers, and finally the output layer. And the number of neurons in the input layer are determined by the number of input features. And this automatically confines the functionality of feed-forward neural networks to handle fixed length inputs. Okay? Whereas the language modeling scenario or task requires to process inputs of varying size. You don't know exactly what is going to be the length of the input text based on which the next word has to be predicted. So you need to go for the RNN, recurrent neural networks. Recurrent neural networks have the capacity to process variable length inputs and can learn shared parameters as a combination of the content as well as the context. So here, the advantage of RNN or suitability of RNN for handling varied length texts increases with the feature of shared parameters. So it learns shared parameters as a combination of content as well as context. Seen so far. Hence, RNNs are explored for language modeling. Compared to other variants of neural networks, RNNs are explored to the maximum extent. The language modeling is a traditional sub of many NLP tasks. The importance of language modeling is very, very high, because if you learn or build the software for language modeling by making certain modifications, by appropriately adapting it, you can solve several NLP tasks. Okay, so these tasks can be either generating the text or understanding the text or converting the text from one language to the other, etc. or estimating the probability of a text. That means how likely for a particular text segment to be the answer for a specific question, etc. Now, everything in NLP is being rebuilt upon language modeling. And GPT-3 is an example of language modeling. And we'll go towards it, starting from looking into the details of RNNs. So the recurrent hidden units, you can say, the neural network will have recurrent neural networks can be represented compactly like this. That means there is an input at a given time step. an input will be given and it will be processed based on U, and then it reaches the hidden state, and this hidden state is having feedback to itself. That means recurrence through with a weight of W. Okay, so the previous weight, that means the H at t minus 1, becomes one of the inputs of the hidden neuron, so that the H of t is calculated in terms of the present input, that is X of t, as well as the past hidden state, that is H of t minus 1. Okay, these two are the inputs for the hidden state. And state reacts, the output O given by the hidden state will be processed through V. It's again the weights, the parameters that needs to be learned. And this output that is generated will be compared to output Y and estimate the loss. Okay, so based on this loss, you will be optimizing during the training process, optimizing the weights U, V, and W during the training process. Yeah. Sure. Okay, let me. Yeah, I'll share it again. Are they shared?
Yes, ma'am.
Okay. Huh? You are at the 90. Okay. Okay. So here in the RNN, you will have this station. And once unfolded, it can be expanded like this. It is expanded, and that means all these details for the activity that goes on this RNN. Okay, so here the middle column in the expanded version represents the present time t. So the hidden neuron at present time will get input from the previous hidden state as well as the present input, that is X of t and H of t minus 1. Both of them are inputs for the HT, and then by processing the HT, you will be getting the output, and this output will be compared with the YT, that is the desired, in order to estimate the loss function. Like that it proceeds. So all of this is Goodfellow, that is deep learning by Goodfellow textbook. So in this, the equations were given. I have explained there are parameters that involves U, V, and W matrices, which are the weight matrices associated with hidden state. U means is associated with the input, and W is associated with the hidden states, and V is associated with transformation of hidden state in order to get the output. Okay, as indicated in these equations, the output is obtained by as a weighted sum of the hidden states. So the weights are defined by V matrix plus a bias parameter C. That is how you get the output OT. Okay, so this will be obtained as a weighted sum of the weight matrix V plus bias C. Similarly, the HT will be obtained as a weighted sum of the input, making use of the weights U, and the previous hidden state H of t minus 1, making use of the weight matrix W. Okay, so that is what is indicated in these equations. So W into Ht minus 1 plus U into Xt added with the bias gives you the At. And when you apply a norm, that is tan H on the At, this is the sum of the input activation. And when a nonlinear functionality is added, you will get the hidden state. Now again, a hidden state, when multiplied with the V matrix, you will get the output. And this is the estimated output. This is the output, and then the output hat, Y hat, is the softmax applied on OT. That means for non-linearity, you will be applying the softmax. The final outcome is a value in the range of 0 to 1 to represent the probability of a specific output. Okay? OT can be anything. There is no limit on the range of values of OT. So that is being converted into the probabilities by applying softmax function. So these are the details of RNN. Now the problems with RNN. The RNNs are good at handling sequences. Hence, the text processing can be successfully done by RNN. But there are certain limitations, like vanishing and exploding gradients. Vanishing gradient is like as shown in this particular figure. When you are calculating the gradients, as more and more distance occurs between a word and its related word. Okay, so there is a lot of time gap between here. What is this? Each column represents a time step. When there are several such columns, then the effect of a particular word on the latest computation will be diminishing. So, some cases, just because there is a long distance, a word has occurred much earlier, doesn't mean that the word is not important for formation of context for another T, a specific position of T. Okay, so here it happens in this case because if you take the effect of the gradients, because the change of weights always occurs in proportion to the gradients. So how do you calculate the gradients? Gradients are calculated. The J is a function that is being minimized. So dou J by dou H1. That means here it is the hidden state at time instant 1. Okay. So when you are calculating the loss function at a time 4, so dou J4 by dou H1 is expressed as multiplication of series of functions, series of fractions. So here, as you go towards the other end, the importance of the fractions that were away from the present scenario will be reduced. Okay, so that is the vanishing gradient problem. So the gradient signals that are older diminish as they are smaller than recent gradients. So the model weights are updated based on the recent effects rather than long-term effects. what would be the gradient here if you are calculating here? It will be just dou H 4 by dou H3, because you need to find the rate of change of the hidden state at time 4 with respect to the hidden state at time 3. So this will be much higher compared to the rate of change of this with respect to H1. Why it is so? Because this will be the multiplication of this with this and this. And all these things are fractions. When a fraction is multiplied by the other fractions, then the total value will be reduced to a great extent. So because of that, the effect of the previous gradients will be reduced. So the gradient signals that are older diminish as they are smaller than the recent gradients. So the model weights are based on the recent effects rather than the long-term effects. So always when this, because our aim is J, the model is adjusted based on the requirements or demands made information in the most recent past rather than the older happenings. So that is the effect of vanishing gradients. And this can be seen, the effect can be seen in the real world scenario of language modeling. So because of these vanishing gradients, the RNNs will only condition up to 7 tokens back, not more than that. In general, RNNs are conditioned only through 7 words, 7 previous words. If a word occurs beyond that, it will not have any effect on the present changes being made in the weights. Okay, so that is a problem. So if you take this example, that is natural language sentence, when she tried to print her tickets, she found that the printer was out of toner. She went to the stationery store to buy more toner. It was very overpriced. After installing the toner into the printer, she finally printed her. What are you going to fill this here? She finally printed her tickets. And what is the distance between tickets and this particular location? There are so many words in between. Definitely not limited to 7 tokens, 7 words. Okay, so in such cases, it's very difficult to fill appropriate word in this particular blank for RNNs because of the vanishing gradients effect. To learn from this training example, the RNN LM needs to model the dependency between tickets on the 7th step and the target word tickets is occurring at the end. Okay, so here there is the distance between tickets and the blank is much higher than 7. So it may fail because of the vanishing gradients effect. So if the gradient is small, the model cannot learn this dependency. The model is unable to predict similar long distance dependencies at test time. So this is the problem with vanishing gradients suffered by the RNN. Okay. And similarly, there is another problem of exploding gradients. In the exploding gradient, suppose if the gradient calculation, gradient at a particular level is very, very high, if the gradient becomes too big, then the SGD update step becomes too big. SGD means stochastic gradient descent. So here it updates the present values of the parameter by making changes indicated by the gradient and the learning rate. What is the learning rate? And J of theta is the amount of change that is observed in the gradient, rate of change of loss Okay, in the objective function, rate of change in the objective function. So this has to be multiplied by rate in order to get the amount of change that needs to be incorporated into the existing, so that new parameters can be calculated. So this is a methodology adopted in the SGAD. But here, if this value is very, very high, then what happens is it is almost like a cliff. You have to get down the cliff slowly rather than jumping. If you directly consider the big gradients as it is while applying the changes in the SGD, changes in the parameters with SGD, is you will be thrown off into a totally different space, and from this space you again have to do, that means you will be forgetting most of the such results that you have achieved till then. Okay, rather than that, what you need to do is slowly you have to change. That means a limit, a clipping should be done. Gradient clipping means if the gradient is found to be, the magnitude of the gradient is found to be very, very high, that means greater than a particular threshold V, then you need to clip the gradient. That means divide the value of the gradient. Okay, what is the value of the gradient? It is very high. It is GV. GV is the maximum gradient that you have obtained. That has to be divided by the threshold value, the present value, so that the amount of change that you will be considering will be reduced. And based on the new G value only, you have to make the modifications to the parameter space. So that is how you can reduce the effect of exploding gradients. Okay, the RNN with LSTM cells overcome these problems automatically. So exploding gradients and vanishing gradients are the problems that pose challenge on the RNNs. So a better solution is provided by the LSTMs. So LSTM means long short-term memory RNNs. So here on step T, there is a hidden state HT and a cell state CT. At every step, you will have hidden state and cell state also. Cell state means it has some memory stored in it. Okay? And HT will be given out, whereas cell state will remain with the particular neuron. So both are vectors of length n. The cell stores long-term information. So the CT will enable the cell to store long-term information. We'll see how. The LSTM can read, erase, and write information from the cell. The cell becomes conceptually like a RAM in the computer. That means it can store information, or it can write new information, or it can erase existing information. So it is almost like a RAM of a computer. That is why they are called as memory cells. The gates are also vectors of length n. What are these? The gates will decide whether to write, read, or forget the content. So for that, 3 gates are there. On each time step, each element of these gates can be either open or close. Open represents 1, close represents 0, or in between. This is the third one. It is not absolute forgetting or absolutely keeping the information, but in between also there is values. So it's a continuum between 0 and 1. The gates are dynamic. That means when to forget or when to keep information or when to rewrite new information. All these things will be decided dynamically based on the context. So the gates are dynamic, their values are computed based on the current context. So these are the features of LSTM that makes it capable of handling these exploding and vanishing gradients automatically. It avoids that problem. So the equations representing the activity at the LSTM cell at time t. We have a sequence of inputs Ex. And we have compute. We will compute the sequence of hidden states HT and cell state CT. Okay, so you have inputs given. Based on the given inputs, you will be calculating the hidden states and cell states HT and CT. Okay, and in order to calculate those things, you have three gates: forget gate, input gate, and output gate. What is the function of the forget gate? It controls what to keep versus forget from previous cell state. So because you have cell state, whether to keep the previous contents or to forget the previous contents, that will be decided by the forget gate. The input gate, it controls which part of the new cell content are written to the cell. Next, the output gate, it controls what part of the cell or output to the hidden state. You can see here in the forget gate, you are calculating. So in all these three gates, they are nothing but the weighted sum of input and the hidden state, the present input and the previous hidden states. But the weight matrices are different, and accordingly, the values will be different. Okay, so they are all combinations of the present input and the previous hidden state. And which combinations that differ? The weights of the matrices will be different. Similarly, the biases are different. So these are to be learned, okay, based on the context. So these values will be continuously changing, and these values are shared, okay, based on once a corpus is processed, the values of these parameters will be fine. And then what is sigma? Sigma is the sigmoid function, or either 0 or 1 or in between. Okay, it's a curve in between 0 and 1. So depending on that, the specific control will be applied. Okay. Next, the other three equations. New cell content. What is the new content to be written into the cell? So new cell content is written as C tilde of T. So this new cell content is calculated by applying tan H on the weighted sum of, like previous case, HT minus 1, XT, and the bias BC. Okay, so previously you are applying a sigmoid function, whereas in this case you are applying a tan H function. So this tan H function gives a value in between -1 to +1, and that is the taken as the C tilde T, and it will be taken as input, one of the inputs, when calculating CT. So part of the previous cell state and some of the new cell state that is recently calculated, present calculation. As a combination of these two things, that means here you are using the forget gate and input gate. So some of the values from the previous cell state according to the contents of the value of the forget gate, and some of the contents of the newly calculated cell state according to the value of the input gate will be combined in order to get you the value of the present cell state. So accordingly, you will be remembering. You will forget some of the past and you will be observing the new happenings in order to form an impression. At present, that means at time t. And once the CT is calculated, based on the value of the CT, you will have the hidden state HT calculated by applying tan H function to the CT, and OT is the output gate value. Okay, so now all these dots represents the dot product. Okay, element wise multiplication of these two vectors, and all these vectors have the dimensionality of n. Okay, where n is the number of time steps. So in this way, the LSTM cells work. So pictorially to show you, this is the LSTM cell, and in this, the input is given xt, and input will be concatenated with ht minus 1, and both of them will be processed through sigmoid function in order to calculate the gates ft, it, and ot. Okay, so these the first three equations, and then by applying tan h instead of sigma, you will get the c tilde t. That is the next equation. Now the c tilde will not be taken as a final cell state, but a combination of past, that means a portion of the past cell state, and the c tilde will be taken here in the plus. So here this is c of t plus t minus 1, a portion of it, through ft. That means to what extent you need to forget, that will be forgotten, and the remaining component will come. And to this you will be adding the it multiplied by c tilde t. So this will be to what extent you have to consider the present happening, and both of them added gets you the cell state. You will make an impression right now that is represented by CT. This will be used in order to calculate the output. So what is the output? You will be taking, this is the OT, and apply the tan H, and then take the CT, and finally you will be getting the HT. So the HT will be equal to tan H applied on CT, as it can be seen here. HT is equal to tan H applied on CT dot producted with OT. Okay, so the CT, when applied tan H, and a cross means it is a multiplication dot product with OT, gives you the hidden state, and it will be stored as a hidden state. So this is the cell state and this is the hidden state. So these are the things that represent the activity at a LSTM cell at a time t. So as the time progresses, that means as you read one word after the other, the time ticks, like starting from t is equal to 1, 2, 3, 4, like that, you will be processing one word after the other. Okay, so in this case, because the system itself, that means the model itself, decides when to forget past and when to forget or retain portion of the information and which portion of the information, etc. You will have reduced effect of the forgetting the long or past information happened long back. So here the LSTM architecture makes it much easier for the RNN to preserve the information over many time steps. If the forget gate is set to 1, then the cell dimension for the cell dimension and the input gate is set to 0, then the information of that cell is preserved indefinitely. Okay, forget gate is set to 1 means you will be having that complete portion of the present cell state without considering what is happening in the present. That means the input gate is set to 0 means you are not allowing the present input, but you are keeping the old state only. So the cell state is preserved indefinitely, permanently. Similarly, depending on the values of the forget gate and input gate and output gate, the LSTM works. It learns when to forget and when to keep, or which particular portion of the statement is important, etc., based on the experience. In contrast, it is harder for a vanilla RNN to learn recurrent weight matrix WH that preserves information in the hidden state. In practice, actually, the vanilla RNN for paucity of time is not discussed, so I want to skip that particular statement. In practice, we get up to 100 time steps rather than about 7. Previously, we have discussed that a normal RNN can keep information up to 7 time steps, whereas in contrast, the RNN with LSTM cells for hidden states, you will be able to keep up to 100 time steps. Okay, so even if a word occurred 100 time steps before, even then it will be in a position to affect the present context if it is imparted. However, there are alternative ways of creating more direct and linear pass-through connections in models for long-term dependencies. Skip connections, etc. So there are LSTMs are very, very successful and they are extensively used for NLP tasks. Very dominant building block. They have become very dominant building block for implementing the NSTL NLP tasks. And in the recent past, that is from 2019 to 23, transformers have become dominant for all tasks compared to LSTMs. Okay, and especially the machine translation conference and competitions. If you take the statistics of that, it happens every year. It's an annual conference. In 2014, there were 0 neural machine translation systems, whereas in 2016, the RNN is mentioned for 44 times. And in 2019, RNN is mentioned only for 7 times, whereas transformer is mentioned for 105 times. So that is the change in the research or the NLP softwares that use transformers as a building blocks compared to LSTM or RNN. Okay, so now we'll move slowly towards transformers. RNNs used for sequence tagging. Yeah, break even now. Okay, sorry. I'll give you 10 minutes break. Any doubts in the topics that are discussed till now? If you have any doubts, you can ask them at the end of the lecture or talk. Now you can take a break because it is already late. You can take a break of 10 minutes. We'll join again at 4:10. Okay? Are you ready?
Yes, ma'am.
Yeah. So till now we have discussed the features of RNN and its limitations in terms of exploding and vanishing gradients, in terms of handling exploding and vanishing gradients, so that we have identified a better building block, that is RNN with LSTM as a suitable architecture for implementing the NLP softwares. Now onwards, if I refer to an RNN, it automatically refers to the RNN with LSTM. Now coming to the applications of NLP. So these are some of the examples. I'll go at a faster pace because these are lighter. So this example talks about the POS tagging, parts of speech tagging of a given text. That is, the startled cat knocked over the vase. So in this, each and every word is identified into one of the categories. Previous session, we had a discussion on POS tagging, the details like identifying the names and then classifying them into one of the categories already recognized, like location, person, date, etc. Similarly here, the parts of speech categories will be the classes to which each and every word is classified using RN. So there are successful systems and RNNs with LSTM are quite sufficient to handle the NER problems, the named entity recognition problems. Second task is sentiment classification. So the input sentence is, overall, I enjoyed the movie a lot. This is the input given, and once the RNN is executed on it, at every time step, one word will be fed, and after processing all the words, that means at a time capital T, where T is the length of the sentence, you will have the hidden state given out by the RNN. And based on the hidden state, you will be classifying the text into either positive class or negative class. That means because the sentiments are either positive or negative. Okay? So in this, there are certain variants. One is either you can rely on the hidden state after processing the last word in the text, or you can take the combination of the outcomes given at every time step, like take the element wise mean or maximum from all the outcomes at every time step, and as a combination of it, make a prediction so that a better classification or the sentiment classification can be done with more accuracy. Okay, so that is another approach, and there is a motivation towards bidirectional RNNs. When you know the complete sentence at once, like in case of sentiment classification, the total sentence or the review will be given to you. So there is no restriction that you need to only rely on the context formation, the text from left to right. when you are processing a word, from left to right, you will have a context. But at the same time, you can even process the same text from right to left also in the reverse order. So if you do that, you can capture the context of a word by processing the words that occur in both the directions. Like at the beginning, we have considered a window for a central word on both the directions. Like that, here also, there is no or limitation for the that they should only rely on the part of the text that is existing or processed already from left to right, but you can also make use of the text that is occurring on the right side of the words also. So this is accomplished by going for bidirectional RNNs. So here in the bidirectional RNNs, you will be having two RNN, that means two nodes. One that processes the text from left to right, and another that processes the text from right to left. And you will have the hidden states separately generated, and both of them are concatenated so that you will have a more elaborate hidden state that reflects the context. And based on this context, always the hidden state represents the context. And based on this context, you will be making more accurate predictions on whether it is a sentiment or whether it is a topic or whatever it is. It can be an opinion, whatever. Okay, so that is the case where you need to go for bidirectional RNNs. But remember, when you are going for more number of hidden states, you will have more number of parameters. You have increased the number of parameters, and the complexity, computational complexity automatically increases linearly. Okay, so that is one aspect. Next thing is the prerequisite is there in order to apply bidirectional RNNs. When you are aiming at language modeling means what? When you are reading, when you are reading, you will be reading only from left to right. Or when you are typing, you will be typing only from left to right. So the information which is occurring to the right of the present word is not available in that situation. So the prerequisite for the applicability of the bidirectional RNNs is that the whole of the text should be available. That means it is not like language modeling scenario, wherein you can only traverse or process the input in a single direction, that is left to right. Okay, so if you do have entire input sentence, then the bidirectional or unidirectional encoding is possible, especially when you are implementing an encoder-decoder models. The encoder will provide you the context, and that encoder implementation can be a bidirectional RNN, whereas the decoder implementation will be a unidirectional. That means left to right, because the decoder generates, okay, it's the outcome. So when it is generating the outcome, it can only be in a single direction. Okay, so with all this, there is a very successful pre-trained contextual representation system known as BET, extensively used in the recent past for building FDP tasks. So here BET means bidirectional encoder representations from transformers. So here the word transformers is the bullet for success nowadays when you're dealing with NLP applications. Okay, we will see the details. Before that, the multi-layer RNNs is another step that can handle complex representations. Okay, so more complex representations of words or context can be formed making use of multi-layer RNNs. In the multi-layer RNNs, you will have the outcome of a hidden state at one layer will be fed as an input to the next layer hidden neuron. Okay, so it is almost like until now we are talking about the unfolding of the hidden states in the horizontal direction. But in the vertical direction also, you will have additional layers added. This allows the network to compute representations. The lower RNNs should compute lower level features and higher RNNs should compute higher level features. So it is almost like a feed forward neural network scenario wherein the hidden neurons at the lower layers will be looking for simpler features, and of simpler features, more complex features will be generated by the later hidden layers. And finally, the output layer neurons will classify the total entity as a single unit. Okay, so like that, here also in the RNNs, if the problem is complex, containing complex features, then you can go for multi-layer RNNs. Applications of multi-layer RNNs. So they are also called as stacked RNNs, and they allow a network to compute more complex representations. And high-performing RNNs are usually multi-layer. And the transformer-based networks are usually deeper, like 12 to 24 layers are used in transformer networks. Whereas in general also, the multi-layer RNNs, we have up to 4 layers. Okay, 2 to 4 layers is the best for encoder RNN and 4 layers is best for decoder RNN. This is known by experimenting. Okay. So the next one is statistical machine translation. So till now we have been discussing the language model. Now the machine translation. Machine translation means you have to convert the text in one language to the other language. Okay, so for this, so many from olden days, the machine translation task was identified as an important thing to be done, and statistical methods are applied. So these statistical methods were explored and they were found to be very, very complex, and they require hundreds of details, and systems had many separately designed subcomponents. So it is not a single system, but in order to translate, so many subparts were there. All of them will be integrated into a framework in order to accomplish the task of machine translation. Okay, and a lot of feature engineering is required, and all this is specific to a specific language, and all of this effort needs to be repeated for each language pair. That means if you are translating a Telugu text into English and you have finished that particular project, a big project, again if you have to do it by converting Hindi to English, all of the task is to be started from scratch. Okay, totally complete repeated work has to be done. So there, it's not a generic approach. So these are the problems. A lot of human effort is required in order to maintain the recent developments in the language. So a better option and a proven option nowadays is the neural machine language machine translation, referred to as NMT. Neural machine translation is a way to do machine translation with single end-to-end neural network. That means a single neural network will be there. If you feed the input to the neural network, it automatically gives you the final outcome. Okay, It contains an encoder component and decoder component. Generally, the model is called as sequence-to-sequence model, and it includes two RNNs. The first RNN is the encoder RNN, and the second RNN will be the decoder RNN. As I was telling you previously, the first RNN can be a bidirectional RNN, and the decoder RNN can be a unidirectional RNN. One neural network takes in input and produces the neural representation. Another neural network put the neural representation. The neural representation captures the context of the or the essence of the sentence, and that essence will be automatically represented as a required language sentence by the decoder. If the input and the output are sequences, we call it as a sequence-to-sequence model. Whenever many NLP tasks can be phrased as sequence-to-sequence, and among them you have text summarization, in which the long text will be given as input and a shorter text will be given as output. Similarly, iteration. So another NLP task which is sequence-to-sequence NLP is dialogue. So in this case, in the dialogue, that means the chatbots, etc. Based on the previous utterances, the next utterance, that means it is a conversationalist. Based on the conversation, the way the conversation is going on, the next segment of the conversation will be generated. And then similarly, the parsing. The input text will be given, the output parse will be given as a sequence. Okay, so text is a sequence and output parse is also a sequence. Like that, a sequence-to-sequence models includes an encoder and a decoder invariably. So the neural machine translation with RNNs looks like this. So here the first one, the sequence-to-sequence model that encodes the input sentence in terms of hidden states. So the hidden state generated at the final time step will be given as input for the decoder. Did you observe this one? The hidden state that is generated at the final encoder state will be given as input to the decoder RNN. And now the decoder RNN start generating one word after the other, such that the text that is generated is equivalent to the text that is given, and the text, the target sequence, is in a separate language compared to the source language. Okay, so this is how the picture occurs, the decoder RNN. So it is again a language model that does a sequence translation. So training a neural network translation. So in this, the optimization will be done by adding the optimization functions at the individual steps. So here if you look at the J1, J2, J3, J4, J5, J6, J7, these are all different loss functions. We have discussed the optimization functions, that is negative, log likely. Okay, so those loss, negative log probability of each and every word will be considered for the target sentence, and then all of them will be added in order to get you the metric that estimates the goodness of a translation that was generated. And based on this, the backpropagation algorithm through time will be applied in order to improve the weights. So the weights are updated throughout the pair of encoder and decoder. That means because the outcome is given by the decoder, and the desired outcomes are available for the decoder, and accordingly the loss function is calculated only at the decoder level, and based on the loss function, in order to minimize the loss or the objective function, you will be updating the weights of the neurons at decoder as well as encoder RNNs. Okay, so that is what is meant by a single system being learned by applying back propagation through time. Okay, so the evaluation metrics for neural machine translation models. So blue compares machine written translation to one or several human written translations. So the repository is available that gives you, for each sentence in a source language, the equivalent sentence in the target language. So this is called the training set. And using the training set, now you will be applying the model. Let the model is learned, and once the model is learned, then based on the contents of the test set, you will be estimating the loss. Okay, so here n gram. So what is it? You will be considering the segments of the text whose length is 1, 2, 3 or 4. 4 gram means 4 words, 4 consecutive words in the text. How many 4 consecutive words in the output that is generated by the model are matching with the 4 word segments available in the human written translated sentences. That determines the precision. Okay, plus a penalty for 2 short sections. So all of this is incorporated into this particular metric blue, and it is useful, but it's not perfect. Why? Because the problem of translation itself is an open-ended problem. That means for a given sentence, there can be several different ways of translating it into another natural language. So you can't say that this is the only correct translated version. Because of that, it's not possible to generate a metric that is perfect for the tasks like machine translation or summarization, etc. Because those tasks itself are open-ended tasks. So a good translation can get poor blue score because it has low n-gram overlap with the human translation. Okay. So just because a translation is, the blue score is less for a given translation, you can't guarantee that it is a poor model, because the metric itself is imperfect. Okay, and the task is an open-ended task. So these are the limitations of evaluating the machine translation models. Okay. So this is the success of machine translation in recent times. Until 2016, there is a slow growth or progress, whereas after 2017, there are revolutionary changes. So from 2017, there is a lot of improvement in the quality of translations developed by these NLP applications. Okay, so these are the scores. Scores were very much improved compared to the previous scores. Okay, This is all possible only because of the neural machine translation methodologies that are incorporated in the recent times. So the advantages of neural machine translations are especially the same method for all the language pairs. This is very, very important. And no feature engineering is required. And it requires less human engineering effort. That means human involvement is very, very less. Only thing that is required is you need a training set of examples in order to learn. Okay? Human intervention is not important. No subcomponents to be individually optimized, because you are optimizing the whole end-to-end model at a time. That means including the encoder as well as the decoder will be optimized in a single stretch. And better use of phrase similarities and better use of context, and it generates more fluent sentences, and the performance is also, that means it is much faster compared to the statistical machine translation methods. Okay, the disadvantages are the neural machine translation is less interpretable. Like all the neural network models have this particular problem of interpretability. Less interpretable they are, but they do the task at a very high precision. Okay, and hard to debug because you can't understand. Less interpretability, because of the less interpretability, the debugging will be difficult, and controlling the whole process will also be difficult. Only thing we can do is by changing the topology. Again, we have to start from scratch and restart the whole training process. It's not changing partial experimentation like that. All of it has to be started to making the changes. These are the disadvantages of neural machine translation, which are in general happens with all the neural network implementations. Next, issues with RNN. So in this, RNNs take order of sequence length steps for distinct word pairs to interact. So as we have seen in the example previously, that is printing, there is a gap of, if the gap between a word, related words increases, then you have to wait to get the context by processing the words in a sequence starting from first word followed by the second word, third word, etc. like that, in only a sequence manner. There is nothing like parallelism allowed. You can't directly process the 10th word or 20th word, etc. That is the problem. Linear order of words is baked in. And then forward and backward passes have a length of the text, number of unparallelizable operations. So at each you have to do the updation of the hidden states, the cell states, etc., etc. So the steps have to be implemented or happen in a sequential manner. So though GPUs are capable of doing so a large number of operations parallelly, you will not be in a position to leverage the potential of the parallel processing capabilities of the GPU in RNN because of unparallelizable operations that needs to be executed in sequential manner. That is the biggest drawback of RNN. Okay, but future hidden states cannot be computed in full before past hidden. Yeah, this is what is being dealt with. Next comes sequence-to-sequence models need better building blocks. So, LS being the building block is good to some extent, but if you have to process large text corpus, then it takes time. And if you are in a position, that means if you learn the model by processing large text, then the model is much more precise and high quality. The quality of the model improves. That means whether you are learning the embeddings or whether you are generating the language model. If the language model is generated after processing trillions of documents, then definitely it will be a perfect language model. But in order to finish that much task, because of unparallelizable operations that are required in case of RNN, it becomes a bottleneck. That is the problem. So the other way of solving these problems is going towards or making use of attention. So here, sequence-to-sequence models need better building blocks. Attention treats each word's representation as a query to access and incorporate information from a set of values. So here, every word will have an attention. So that amount of attention that needs to be given for a word will be calculated while representing those words. Okay? We saw attention from the decoder to encoder. And based on the attention that needs to be, that is estimated by an encoder and given as input to the decoder will be in a position to generate the sentence in case of the sequence-to-sequence modeling like summarization or whatever it is, the language modeling, etc. So an advancement is a self-attention within a single sentence. So here, the number of unparallelizable operations does not increase with sequence length if you rely on attention. The maximum interaction distance will always be order of 1. It is constant, since all the words interact with each layer, at each layer. So here, these are all the embeddings, and all these embeddings are available to the first layer neurons. And similarly, all the outcomes at the first layer will be given to the second layer. That means here, there is nothing like waiting for a sequential processing. Okay, all words in the text will be processed simultaneously if you go for attention as a concept for building the model. Okay, attention as fuzzy lookup in key value store. So here, this is the attention. In attention, the query matches all the keys softly. So here there is a store which contains keys and their values. And the query is the representation of the word. And you need to learn this. That means an answer for this query is the representation of the word itself, which is nothing but a specific combination of values. The key values are multiplied by the weights and sum. So the weighted sum of key values will give you the output for a given query. So it is like this. Estimating the self-attention of the words in a sequence. For each word WI, let Xi is equal to the embedding of the WI. Okay, where E is the embedding matrix. Now transform each word embedding with weight matrices Q, K, and V. So there will be 3 weight matrices. Like in LSTM, you had U, V, W. Instead, in the attention models, you will have Q, K, and V as different weight matrices. So these are all of D into D dimension. Okay, so here from these weight matrices, the Qi is equal to Q into Xi. These are all queries. What is Xi? Xi is the word's embedding. From the embedding matrix, you can get the embedding of the specific word. So that is nothing but Q into Xi. So that is a Qi. Next, keys. From the keys matrix, you will get the specific row. That means the dot product of the K into Xi. Similarly for the V, compute the pairwise similarity between keys and query. So it is almost like a table lookup. Yeah, a table lookup. So this is all the table. You need to compare the query with the key, and accordingly you have to use the value. So here query with the key. So if you take the dot product of the query and the key, you will get the similarity between the query and the key, and accordingly get a probability. Apply softmax function, and its output is represented as alpha. So this is going to be the weight that you are going to give for the value associated with the word. So value, it is a VI. So this value will be given alpha weight. What is alpha ij? Alpha ij is the similarity between the query and the specific word. Okay, so as a combination of, that means the weighted sum of values based on the query OI generated, compute the output for each word as a weighted sum of values. Like that, you have to represent the words made of the attention methodology. So here, the barriers and solutions for self-attention. For every word, attention is calculated at every time instant based on its position. Now the barriers are like, in order to use the attention for language modeling, the barriers are, it doesn't have an inherent notion of order. So this can be overcome by adding the position information to represent the words. So the input contains the word embedding as well as the position of the word in the text. If both of them are given as part of Xi, which is the input representation, then this problem will be overcome. That means it doesn't ignore information. Which word occurs at which position will be automatically incorporated into the input representation. The second barrier is no non-linearity for deep learning. It is all just weighted averages. So a non-linearity can be included by having a feed-forward network at the end of self-attention output. After getting the output, that is by multiplying, the output is obtained by multiplying the values with the similarity estimate. Okay, so you'll have an output. So for this output, if you give these outputs to a feed-forward neural network, automatically feed-forward neural network has the activation function that converts the given input into a non-linear space. Okay, so that will be overcome. So the third barrier is need to ensure we don't look at the future, because if it is a language, if you are aiming to build a language model making use of the self-attention, the future words should not be seen prior. Because in this self-attention model, all the words are being read at once. The future words will also be read as part of it. So that has to be avoided in order to use the attention, self-attention, as a basic concept of language model. So in this case, what you will be doing is, some of the words will be masked out by artificially setting attention weights is equal to 0. So the weights will be automatically made equal to 0 for some of the future words, so that the future will be automatically masked, and accordingly you can use this self-attention as a building block for developing language models. So the minimal self-attention building block will have the position representation, a non-linearity represented, and the masking is also done. So the basic operation of self-attention added with the sequence order, and then you will have, after the attention, you will have a feed forward network processing the outcome generated by the masked self-attention. So here the masking will be done in order to stop the model from reading the future values. So all the future values will be masked out. So in this way, this self-attention building can be used as a building block. So again, one more advancement is multi-headed attention. Instead of focusing only on a single perspective, you can go towards multiple perspectives by while reading a text segment. So here, if you take the sentence, I went to Stanford CS 224N and learned. The same sentence is also given here in the multi-head attention model. Certain aspects will be taken into, they will be considered by one head, and certain other aspects will be considered by the other head. So in this particular thing, the attention head 1 attends to the specific entities, that is the names, which class, which institution, etc. Whereas the attention head 2 attends to syntactically relevant words. That means what has happened. That means I went for learning. I went and learned. Like that. Okay, so this is one aspect, and these are another aspects. That means like that. If you go for multi-headed attention model, it will be computationally efficient. You can finish the, just wait. You can finish it much faster. So here, simply the time is over now. I'll be closing with the last slide. Like, transformer decoder with multi-head attention involves this type of structure. So now the decoder inputs will be given like the word embeddings followed by add position embeddings, as I was telling you, because the self-attention doesn't have any concept of sequencing or ordering of the words. The ordering of the words will be given as input in terms of position embeddings. So the word embeddings and position embeddings put together becomes the input for the attention model, and this will be fed to the masked multi-head attention. In the multi-head attention model, you will have different attention models working on different perspectives of the input sentence, as I was talking about in the previous slide. One aspect can be the syntactic aspects, and another aspect can be which entities are involved, and another aspect can be are there any sentiment, is the sentiment positive or negative, etc. All these things. Okay, that is multi-headed attention. And then automatically asking the future words, and then followed by add and norm. This is the layer wherein you will be having residual connections and layer normalization added. Okay, so here you will be adding a feed forward neural network. That is one aspect. And then the residual connection is represented by this line. Residual connection means what? Directly, whatever is the original input, that will be given to the next layer. That is called residual connection. Whereas to this, you will have the outcome of the multi-headed, masked multi-headed attention will be added with the original input. And the other aspect is layer normalization. So in the layer normalization, what happens is the weights will be here. This is the residual connection, pictorially shown. Residual connection. The layer is there. The xi minus 1 were given directly to the layer in order to produce the next output, that is xi. In residual connection, what you will be doing is xi minus 1 will be processed through two links. One is the direct connection, and another one is the final result of the layer, and both of them will be added. Be getting the x at time instant I. So in this, the work of the layer, that means it is like diff sets. The work of the layer, work to be done by the layer will be reduced, because what you need to, that means the layer has only to, the layer will focus on what is the difference, how much difference is to be made on the original value, because at the end the original value is anyway be added to the outcome of the layer in order to produce the xi. Okay, because of that, the total computation, amount of computation required will be reduced, and the training can be finished much faster. And the results were shown here on a specific application. That means a ResNet is a framework that utilizes these residual connections, and in this an image is generated without residuals and with residuals. If the image is generated, the image of a landscape is generated with residuals, the quality of the picture is much higher compared to without residuals. Okay, the gradient is great through the residual connections. So here, what is a gradient? It will be absolute 1. So bias towards identity function. Next is transformer encoder. In this layer normalization, how do you normalize a layer? The weights of the layer normalization is a trick to help models train faster. Here also, the computational efficiency will be achieved by going for layer normalization. Cut down on uninformative variation in the hidden vector values by normalizing to unit mean and standard deviation within each layer. So what you will be doing is find the mean and standard deviation on the values of x, and then apply z-score normalization, so that the off normalization you will have normalized, that means the distribution of values following the normal distribution. If you go like that, the computational efficiency is observed. So after doing all these things, you can have the architecture of a transformer decoder represented using this particular picture. So the word embeddings added with positional embeddings will be fed to the first block, and this block contains, all of this is a single block, and this block contains a masked multi-head attention model followed by the residual connection and a layer normalization added in order to introduce the non-linearity into the outcome generated by the attention model. Finally, you will have the linear feed forward network in order to make it non-linear. Okay, so whenever you are going through a layer, the add and normalization. Add means it is the residual connection, and layer normalization. This block will always be there at the end of each layer, and whole of this is considered as a single block, and several such blocks will be stacked one over the other in the transformer. And finally, you will have, after multiple blocks, you will have a linear summation of the outcomes, finally processed by the softmax in order to generate the probabilities. So these are all the building blocks, okay, in the transformer decoder. Okay, so this defines the transformer architecture for implementing a decoder. Similarly, the encoder. In the encoder, there will be no masking in the encoder. What is the purpose of encoder? Encoder can process, that means at this, when you are encoding the text, you will have all the information available, that is left to right and right to left. All the details are available. That is why you will be applying bidirectional LSTM when you are using LSTM as the building block. So in the transformer architecture, there is nothing wrong in reading all the words at a time when you are at the stage of encoding. Whereas when in case of decoder implementation, because in the decoder only the previous words are known, but the later words are not known. You can only process the words that are processed until the time t, but not beyond. You need to go for a masked multi-head attention model. Whereas in case of encoder, you don't require to mask. So no masking will be there, except that the other things are similar. Okay, the encoding of input words added with positional embeddings, and this will be fed, and then there is a residual connection whenever there is a layer, and in between the first thing is multi-headed attention followed by layer normalization, followed by the feed forward network, again followed by layer normalization and residual connection, and finally a linear combination of the inputs processed through a softmax in order to produce the probabilities. Gives you the probabilities of expected words. Out of those probabilities, based on these probabilities, you need to generate, the decoder has to generate or find one word after the other, such that the optimization function for a given sentence will be minimum. For that, you will be going for team search methodology. So on the similar grounds, you have the encoder-decoder architecture. We have discussed individually both of them. In the encoder-decoder architecture, you will be going for cross attention. That means the outcome that is generated by the encoder will be given as input at the second layer, the multi-head attention. Okay? Until then, at these two stages, it is a self-attention, whereas at this stage, it is a cross-attention. So the results of the transformers are promising. You have seen the rung values. The rung is again, it is the ratio of the number of longest sequences that were matched between the human generated outcome and the machine generated outcome. So here, this particular values, as they are higher, it is better. That means they are more towards human generated. So here, if you when you compare with the sequence to sequence attention model, it is only 12.7, whereas with transformer versions, it was raised much higher, 3 times almost. Okay? So in that way, it's a proof that for document generation, the transformer models are the promising direction. Okay, so the next aspect can be pre-training the models, because a lot of time will be required in order to generate these word representations. An approach like transfer learning helps you in keeping the model that is already generated and then refining the model so that according to the specific NLP task, so that the task or software development can be done much faster with much ease without reinventing the wheel again and again, because most of the parts are common. If you take the movie, the embedding for the movie is always the same, irrespective of the context in which the word occurs. So for certain words, the representation of the word is not very sensitive. In certain cases, it is sensitive, especially for the words which have multiple senses or meanings. Then the context is very, very important. So in such cases, you have to redefine the representation according to the task that is being dealt with, but not for all or each and every word. So it is advantageous to make use of the pre-trained models as an initial or quick start and improve them. That means by fine-tuning them, you can finish implementation of the NLP tasks. So that is a more efficient idea. So that is also explored in the recent past by the NLP researchers to a great extent. So with this, I'll close today's talk on NLP. Now, I'm open for questions. Okay. If you have any doubts. First of all, did you follow the lecture? Any of you could get something from today's lecture? Did you follow?
Yes, madam. Yes.
Okay. So are there any questions? So this transformer is the building block for developing the Chat GPT and all the recent language models, which are very, very successful in handling natural language with the people. Whether you construct a dialogue model, a conversationalist. Please ask if you have any questions. Don't hesitate. So all the topics that are covered in today's lecture are very, very recent topics developed in the last 4 or 5 years after 2017. Thank you. Thank you, Jaisuma, for giving me the opportunity to share my knowledge. So for this lecture, actually it made me, it's a stimulation for me to read again so many papers, books, etc. Learn something, add to my knowledge on NLP. I thank you for giving me the opportunity for learning as well as sharing. Thank you, one and all. No one is asking any questions.
I'm Sinisha.
Yeah.
Thank you so much, ma'am. This talk covered the entire topics on natural language processing. And it is very detailed and it is very useful to us, ma'am.
Thank you. Thank you. So it will be useful if you are going towards research or further exploration in NLP in depth, like whether it is for implementation or so. Thank you.
Ma'am.
Okay.
Okay, ma'am.
Thank you.
I would like to express our sincere appreciation to Professor M. Sashi ma'am for generously sharing their time, knowledge, and experience with us. Professor M. Sashi ma'am has provided us the valuable takeaways that will undoubtedly benefit the profession. Thank you, ma'am.
Thank you. Okay. Thank you. And not very busy schedule, but my throat is having some. I have some problem with my throat today. That is stopping me from expressing in a better manner. I think my throat is a bit harsh now today. That's the problem. Except that there is no problem. I enjoyed thoroughly the total learning process and delivering my knowledge. Thank you. Thank you.